Remind you that we have a town hall meeting today at 4:45, just right after the second talk, where we'll discuss what to do beyond the formally organized workshops. So please stay. There'll be, if you would like to propose something fun, playing music, game night, or doing informal seminars. There are much deeper topics that we would like to discuss. Maybe we can do that outside of the scope of a formal talk. So please come after the second presentation today. It's here. Is it going to be here, right, Dan?
No, 116.
Oh, 116. Sorry. Yeah.
116. 2 doors to the right. Something like this.
And I think there will be food. So if that gives you some incentive to stay
We ordered
around.
snacks. We do not order alcohol. Sorry, folks. This is a topic of discussion during the town hall meeting. How do we solve this problem?
Yes.
Bring a little thing in our pocket.
Exactly.
Apparently we can do this. I don't know. Antonina will tell us. And also we ordered snacks, but they asked me for a phone number. So if the snack people contact me, I have no idea what to tell them. So hopefully the snacks will show up. Yes. If I get a phone call, I don't know what to tell them.
You say yes.
Okay.
All right. Okay, so we have Virginia back on the fine-grained complexity track, and it's on dynamic graph algorithms, which is basically incremental view maintenance, which is dear to database research.
Thanks a lot. Okay, yeah. So I will be talking about dynamic graph problems and fine-grained lower bounds. But before that, a detour. Okay. So what I'm going to tell you is something maybe we should have said yesterday, because you guys really care about general problems. So let's quickly talk about general problems. Dan was talking this morning, and this is something that is known. Okay. So when we talked about min plus product yesterday, Nicole talked about it and about transitive closure, which is the all pair shortest path problem. Actually, the same thing that she said holds in general for these closed idempotent semirings, where closed semiring, Dan mentioned it. And it's actually in this book by Aho, Hopcroft, and Ullman on these pages. You can go check it out. And it generalizes these results of Fisher, Mayan, Furman, and Monroe. Basically, they showed that this theorem holds for the Boolean semiring and the tropical semiring, but it more generally holds for all idempotent closed semirings. And it is that the complexity of computing the product, matrix product over that semiring is exactly the same as that for the transitive closure.
So here closed.
Closed is like the star operation exists. Yeah, according to the book here. Yeah. Okay, so I wanted to say this. Another thing I wanted to say is that in this paper of Ryan and I, we wrote this paper about fine-grained reductions and subcubic reducibility. There is a more general form you can prove about the relationship between this negative triangle problem and all pair shortest paths. And you can read this here. You can define like a set of integers that are between minus m and m for some positive integer m or infinity. You add infinity. You pick any binary operation that has left multiplicative identity and a 0, basically. Then the following, you can consider the following problems: computing this min O dot product, matrix product verification, which is given 3 matrices A, B, and C, and you want to know if the min O dot product equals C. And then you can define the negative triangle problem, which is given a tripartite graph with weights from this R. You can define the problem: does there exist I, J, and K, so that Wik O dot Wkj plus this plus, because we're over the integers over here, is defined that this is less than 0. This is exactly negative triangle if you think about the min plus product. And if you have that, you can prove this theorem that the complexity, that all these problems are subcubically equivalent. So if you have a subcubic time algorithm for any one of them, you can solve the other two. So you can prove these more general theorems. This is true. We like to focus on specific problems, but if you look at the reductions, they're true more generally. Okay. All right. So that was my detour. So if you have any more questions, we can talk about it. So today I'm going to focus on slightly different problems. These are dynamic graph algorithms. What is a dynamic graph problem? All right. You have a graph. It could be directed, undirected, weighted, unweighted, whatever. And you want to store some information about it. And you need to be able to support updates. Insert an edge, delete an edge, update the weight of an edge, stuff like this. Or you could insert a vertex with all the edges coming out of it, or delete a vertex with all the edges next to it. And then you also need to support queries. Every query defines the problem that you are solving. For example, you could ask queries, can a vertex S reach another vertex T in your graph? That's the reachability problem, or transitive closure. How many connected components are there? And this changes when you insert and delete edges. What is the diameter of the graph? This can change drastically, and so on. There's many of these graph problems. Each of them has a dynamic version with various edge updates or vertex updates, and so on. There's also partially dynamic algorithms, okay? A fully dynamic algorithm supports both insertions and deletions. A partially dynamic algorithm could be incremental, which means only insertions, or it could be decremental, which means only deletions. Now, there is kind of an overload of definition here, because in graph algorithms, when we mean incremental, it's only insertions, but I guess in databases, it's both, right? Okay, I just wanted to point this out. Okay, here's an example. I have an undirected graph. I can insert or delete edges. And at any point, I can point to two vertices S and T, and I want to know, are they connected? Are they in the same connected component? And now, as I insert edges and delete them, there's a trivial algorithm to update the answer. One way is, I insert an edge, I ask, and then when I insert the edge, I recompute the connected components. I could do that. Or during the query, I check, is there path from S and T? And that would be a linear time operation. I have to look at the whole graph, run BFS, DFS, and so on. That would be very expensive. I don't want to recompute. Fortunately, there are very fast algorithms for this problem. The most recent one that I could find could perform insertions and deletions in log n times log n squared per update. I guess amortized, and this much time per query. N is the number of vertices here, but it doesn't matter because M, is most n squared. This is super fast, much better than order n. There is a lower bound under the cell probe model of computation that you need log n queries to the memory in order to answer, to update the data structure. Yeah. Actually, this algorithm, it doesn't care. You can change, every query could be about a different S and T. S and T are not fixed here necessarily. Yeah. So we're very close to the lower bound. Yeah.
This is very close to what the current database is. So I wanted to ask you about the query time. This means that if I'm asking now if S and T are connected, I don't get the answer immediately. I need to wait so much.
You have to wait this much time. Yeah, this is a extra running time per query. Yeah, it's not constant. Yeah, but this is an undirected graph. Okay, this is very important. Let's look at directed graphs.
Amortize the word.
That's amortized. Whatever. Let's forget about amortize right now. Okay. Okay, so let's look at directed graphs. Right, the same problem, but now your graph is directed. You can insert and delete edges, and we ask, can S reach T? Okay. Again, the trivial update time or query time is easy, right? You can still recompute after each update or each query, and the same lower bound still applies. You still need to do log n time per update. But the best known algorithm to support these things has a polynomial running time. Okay, the current best is n to the 1.41. It uses matrix multiplication. but it is very far from log n. It's exponential in the lower bound. And so it's, in fact, the question that we had earlier, the same sort of thing holds even if S and T are fixed. Okay, even if we only have this query about a single pair, the same situation arises. Okay, and why? Okay, so I call this ST reach. Okay, maybe you have a different name for this problem, ST reachability. Why is directed reachability hard, whereas undirected reachability is easy? So for the directed graph case, it seems like we're stuck at performing polynomial time updates, whereas in the undirected case, it's super easy, with the current techniques at least. Okay, so this is one example as a motivation, and we'll see some more as we go along. So I'm going to give you some introduction to some fine-grained lower bounds for these dynamic problems, and then I'll give you some constructions that are very simple, so you can see how simple it is, at least, with our framework. Okay, so here's many examples. This is the ST reachability problem I talked about. This thing is, given a directed graph and a single vertex, tell me how many nodes that vertex can reach, the number of nodes reachable from a single source. This is compute the strongly connected components. This is compute the size of a maximum matching. This is the same connectivity problem. Are S and T connected, but now you have vertex updates instead of edge updates. And this one is give an approximation to the diameter of the current graph. For all of these, you can do the trivial thing and recompute after the update or after the query. This is linear time for all of these problems, except for the diameter, in which case you have to run all pair shortest paths. M is the number of edges, N is the number of vertices. Yeah.
For the partially dynamic situations, are these roughly the same or are they drastically different?
It varies problem to problem. That's a great question. Yeah, we can discuss this. All right, and the lower bound is still this. The unconditional lower bound is log n.
Where does this come from, the lower bound?
It's a very nice lower bound by Petrashko in the main. They have a nice paper where they talk about how many queries you need to do to your memory in order to maintain your problem. Yeah.
So it's an oracle model.
It's the cell probe model. It completely disregards computation. It's only about memory accesses.
Thank you.
Okay, so there's a huge gap between linear and logarithmic, and we want to give an explanation. And we'll do that with fine-grained complexity and other assumptions that we have. Okay, so let's start back from 2010. So Petrashko was very interested in this discrepancy, and he looked at the three-sum problem, which I defined yesterday, given n integers. Let's say do 3 of the numbers in the set sum to 0, and the hypothesis is, again, that you need basically quadratic time to solve this problem in the word-gram model. And he devised some very nice reductions from three-sum to these problems, ST reachability, the number of nodes reachable, and connectivity under node updates. And he showed that for these problems, under the three-sum hypothesis, you need some polynomial running time, some polynomial update time, or some small a bigger than 0. And this is really good. It gave the first conditional polynomial lower bounds for problems like these under a natural hypothesis. It's a very nice set of reductions too. So then you wonder, this is m to the 1 and this is m to the a. Why can't a be 1? So then we tried to make a 1. In a set of 2 papers, we brought a up to 1/3. So basically, for all these problems under the three-sum hypothesis, your update time or your query time has to be at least n to the 1/3. But again, maybe you can still beat linear time. No, we don't know. And these from threesome, we didn't have any conditional lower bound for the approximate diameter problem. So, okay. this perhaps suggests that we need a different hypothesis, right? So which different hypothesis? Well, here's one. Okay, so here's a Boolean matrix multiplication problem we've seen before. A and B are Boolean matrices, compute the OR of n's per entry. The fastest known algorithm is an algebraic algorithm that runs in n to the currently 2.372 time. This, from this year. It used to be 2.373, now it's 2. Great. Unfortunately, even though this is a very nice constant and it's subcubic, these techniques that we use here to improve the matrix multiplication exponent are currently extremely impractical. So they're not used in practice at all. And because of this, people keep talking about combinatorial algorithms, which basically says ignore Virginia's techniques and you do something better. So do not use algebraic techniques because they incur these huge overheads. And this is, of course, a completely not well defined, because I could take Strasson's algorithm and make it look combinatorial. You would never know, but whatever. Let's stick with this. We want a simple algorithm, and the best simple algorithm currently is n cubed, runs in n cubed divided by log n to the 4th time by Ho-Chang Yu. So it is not nice and not n to the omega, but it's simple and beautiful, and it runs at this much time. And there's this hypothesis, again, with this completely undefined notion, that if you can get that there are no nice subcubic time algorithms for BMM, truly subcubic. So basically this hypothesis says that if you want a truly subcubic algorithm, it will have to be like one of these, something really horrible and impractical. Yeah.
Do you have some kind of favorite combinatorial definition, or is it just, you use it?
People have tried to give a definition, but you can always massage, for example, Strasson's algorithm to make it look like it is combinatorial. So it's undefined, but you look at it and it looks nice, so maybe it's combinatorial. But anyway, so there's this hypothesis about these algorithms that a simple algorithm has to basically run in like n cubed over some polylog n time, or n cubed to divided by 2 to the square of log n or something like that. Okay. So now we showed that if you believe this hypothesis, not believable, this was by me and Amir Aboud, you can actually get a conditional lower bound of this flavor. So basically, what does this mean? So it's undefined, but it means that if you want to beat this upper bound, this trivial upper bound of recomputation, you should be using matrix multiplication. That's what it means. That's all it means. So anything that doesn't use matrix multiplication somewhere in there will have an update time that's roughly linear. So you might as well recompute. For approximate diameter, this was not mn. We were able to get like a square root of n lower bound. It's still not very satisfying because maybe I can use matrix multiplication, so what? So it gives a tight lower bound for some problems, but it's only for combinatorial algorithms. Because of this, because people were very unhappy with this combinatorial notion, a new problem was defined. So by Hensinger, Königer, Nanun Kai, and Sarunarak, they said, you know what, we're talking about dynamic algorithms. So why should our lower bounds be from a static problem? Let's define a dynamic problem that is about Boolean matrix multiplication. So this is the online matrix vector multiplication. What is that? You're given a Boolean matrix A, you can preprocess it. After you preprocess it, you get given Boolean vectors v1 up to vn. Every time you see v sub I, you have to compute a times v sub I, at least return it. So you preprocess your matrix, you store something, and that should allow you to compute the inner product of a and vi very quickly, immediately after seeing vi. All right. It's basically Boolean matrix multiplication because you have n vectors, but it's one by one, column by column, you see the matrix. Now, Ryan, before he even saw this definition, he had been working on trying to pre-process Boolean matrices and computing A times VI, and he gave this algorithm that runs an n squared over log n squared time for this problem. And you can do a little bit better. His APSP framework can make this log squared of n into 2 to the squared log n. You can do better than that, but still it's not quadratic. So the OMV hypothesis is that this problem requires quadratic amortized time to compute these inner products. In other words, the total time to do the Boolean matrix product is n cubed. This is completely analogous to the BMM hypothesis, except we now removed the combinatorial notion in front and we replaced it with a dynamic version, an incremental version of BMM. Okay. This makes sense? So this is a new hypothesis. And notably, all of these conditional lower bounds, all these reductions we had from Boolean matrix multiplication, they still work because they were actually doing it from this problem anyway. We were looking at the problem column by column, so they still work. So now we get the same conditional lower bounds from this OMV hypothesis, and now we no longer talk about combinatorial algorithms. So against arbitrary algorithms, if you believe this hypothesis. And we still have this issue that we don't know, it doesn't correspond to a very high conditional lower bound for diameter. All right, so now, what about diameter? For diameter, oh, yeah.
So, does the BMM hypothesis imply the OMV hypothesis?
Sorry?
So, does BMM hypothesis implies the dynamic version of the hypothesis?
Does the BMM hypothesis imply the dynamic version? Well, if you can solve the OMV problem in cubic time, yes, you can solve the BMM. But maybe use algebraic techniques, so it doesn't. So if your algorithm is combinatorial for OMV, yes, it will. But then if somehow manage to use matrix multiplication, I don't know how, then it wouldn't. Okay. So now we want to discuss diameter, and as Nicole presented a reduction from orthogonal vectors to diameter, so it's natural that we consider a reduction in the dynamic case. Okay, and maybe in the dynamic case, we would be able to show a lower bound of this. I just want to point out this order mn is for after every update, you're recomputing all pair shortest paths. This is insane. Okay, this is like, for dense graphs, this is cubic time after each update. Okay, linear time, I understand, but mn. So I really, for a while, didn't think this is the right answer. I thought, we should be able to do something better here. But as you will see, if you did, then you would resolve strong XCH. So that would be very interesting. Okay, so just a recap of what Seth and Olivia are. You've already seen it several times, but again, the strong exponential time hypothesis says that there's no 2 to the 1 minus epsilon n time algorithm that solves k-sat for all k. And OV, you have two, today I'll define them as two sets of vectors, both of size n. Yesterday you saw it with one set, but this is an equivalent formulation. Okay, now you have two sets of n vectors, binary over small dimension, d is n to the little of 1. Decide if there's a vector in A and a vector of B whose inner product is 0. Since this is equivalent to the previous version, you have the same hypothesis. OV requires quadratic time, and Ryan's reduction that I presented still says the strong ETH implies this hypothesis. Now, I'm showing this to you because now I'm going to generalize it. Okay, we had two sets for orthogonal vectors. There is a problem called k orthogonal vectors, in which case, where you have k sets of n vectors each. Again, binary over small length, and you want to know if there's a vector from each set, so that their generalized inner product is 0. The generalized inner product is defined as the sum of all coordinates over the product of the vectors in that coordinates. And being 0, because the vectors are binary, means that for every coordinate, one of these vectors must be 0. Okay, this is K of V. You look at, so the K orthogonal vectors hypothesis says that this problem requires n to the k time. Okay, and if you look at Ryan's reduction and massage it a bit, you will get that strong ETH implies a K of V hypothesis. Now there's, you might ask, you know, how does K of V relate to the original OV? Well, you can reduce any K of V to OV. So the two set OV problem is the hardest out of these. So you can reduce all the K, you can reduce K to K minus 1. So it gets harder as K goes down. So this is the problem. Questions here? All right, so now if you assume strong ETH or KOV for some K that you choose, then you still get linear conditional lower bounds for these problems. You don't get anything for ST reach or maximum matching, at least I don't know how, because the quantifier structure is different. But you do get an MN conditional lower bound for approximate diameter. So if you believe the strong exponential time hypothesis, the best you can do to approximate the diameter dynamically is to recompute all pair shortest paths after each update. Which maybe should have you believe the strong ETH is not true. Okay, so this was my introduction. Questions, yeah?
Do we get anything if we wiggle the approximation ratio?
Yes, yeah. I will show you about approximation 4/3. The same holds for 3/2, and you can probably get other stuff in between. I haven't actually worked it out, but it will be kind of similar to what Nicole showed as an approximation hardness trade-off from yesterday. Yeah. Okay. So what I'll do now is I'll give you 3 little examples of constructions to see how simple things are once you have the right problems to start from. And all of them will be from orthogonal vectors or KOV for some K. The first one will be for maintaining the number of nodes reachable from a source in a directed graph. Okay. Dynamic single source reachability. Given a source S in a directed graph, which nodes can S reach? This you can do in linear time, right? This is not the dynamic problem. This is the static one. In the dynamic one, we delete and insert edges. We want to know how many nodes S can reach. I don't need to know which ones. I just want to know how many. Okay. The trivial solution is after each insertion and deletion recomputed with DFS, or during the query time you can do it. Either way, it's linear time. Sankovsky in 2004 showed that if your graph is dense enough, you can do a little bit better using matrix multiplication. So you can get n to the 1.5, let's say, update and query time. Which, you know, if your graph has at least n to the 1.5 edges, is better than recomputing from scratch. And there's no non-trivial solution for sparse graphs. Yeah.
What happens if you only care about insertions? Can you do that?
Good question. I think so. Yes. For insertion, you can. Yeah. Or I think, yeah, for only insertions, you can. But once you have fully dynamic, it becomes interesting. Yeah. Good. Okay, so what I'm going to show you is this theorem. If you can get sublinear, truly sublinear time queries and updates for single source reachability, then you can solve orthogonal vectors in subquadratic time and set this false. So this is for the standard orthogonal vectors, and we'll just do the reduction. This is how the reduction will go. We will create, given us an instance of orthogonal vectors, we'll create a graph, an initial graph, which your data structure can pre-process. Okay? And after that, we will have a stage for every vector in the orthogonal vectors instance. What does the stage do? It inserts a very small number of edges, d edges, which will correspond to the number of dimensions in your vectors.
And to the original one on the right here. Yeah.
What is that one doing there? Oh, thank you. There's no one there. It's just a little one. Yeah. So you insert this many edges, which is the dimension without the one. And after you insert these edges, you have a single query. You have asked, how many nodes can I reach now? It'll say something. Then we'll remove these inserted edges and move on. And from all these n queries, we will somehow figure out whether there's an orthogonal vector pair. And queries n to the 1 plus little of 1 updates. Okay. And if I can set this up, because the number of updates is this much, and the number of edges in the graph will be n to the 1 plus little of 1, then n to the 1 plus little of 1 to the 1 minus epsilon will be roughly n to the 1 minus epsilon time query and update times the number of queries. We'll get n to the 2 minus epsilon time, and we'll solve set. All right, so let's do it. So this is the graph after pre-processing. Let's go through it. So every vector will have a node on the left. We have coordinate nodes over here, and we'll have edges from right to left, from a coordinate to a vector, if the vector has a 1 in that coordinate. So every coordinate will have a 1 from all the, every vector will have an edge from every coordinate that it has a 1 to. And then there's no other edges. So this is the original graph you create in your data structure, pre-process it. This is the source, currently has no edges, and we'll always be asking queries about how many nodes this node can reach. All right, now we start a stage for a vector u in the orthogonal vectors instance. What do we do? We'll add some edges from the source to the coordinates. We'll add an edge from the source to a coordinate e if the current vector u has a 1 in that coordinate. So we add some edges exactly to the coordinates for which the vector u has a 1 in. All right. What happens here? So S, the source, can currently reach every coordinate that it has a 1 in. And we know how many there are because this is the number of edges we inserted. Let's call them x. S can also reach every vector that it is not orthogonal to. So it can reach a vector here if it shares a coordinate in which it's 1. So it's not orthogonal. So it can reach everything it's not orthogonal to. And you cannot reach anything that it is orthogonal to. So there exists some vector here, v, that is orthogonal to you if and only if the number of nodes reachable from S is less than n plus x. So when I ask the query how many nodes can S reach, if I get less than x plus n, I know that there's an orthogonal pair involving u, and I can even stop and return. Otherwise, I delete the edges, move on to the next u. I have n times d updates. So d updates, 2d really, d insertions and d deletions roughly per vector, and there's n queries. And the number of edges altogether is order n times d, because there's only an edge whenever a vector has a 1 in some coordinate. So it's nd. D was tiny, it's n to the little of 1. So this nd is n to the 1 plus little of 1. And therefore, if we can solve this problem in subquadratic time in the number of edges, this will be subquadratic in n, which then can solve OV in subquadratic time as well, and therefore set will be false. Okay. It's extremely simple, as you can see. You just kind of insert and delete and whatever, and it's the same problem in disguise. Questions about this? Yeah.
What's the role of the deletion?
Oh, I have to delete edges to encode the next vector. Right, so I encode vector u by the ones over here in it, and then I delete them and insert the next vector.
But it's directed edges, right? So
Yeah, it's directed. Well, like if I leave these edges in here and I insert another edge here, then it won't encode the next vector. So I won't be able to tell whether there's something not, that's a problem. Make sense? So I need deletions. All right. Good. So this is a simple example. Now I'm going to show you something for the strongly connected components, which will be very strange. It will say that even just maintaining whether the number of strongly connected components in the graph is more than 2 is difficult. Let's talk about strongly connected components. In the static version, the strongly connected components in a graph, like here and here, can be found in linear time in a graph with images, DFS, and so on. In the dynamic algorithms case, you want to insert and delete edges, and you can support maybe one of two queries, maybe both. One type of query is, are U and V in the same strongly connected component? And the other one is, how many SCCs do you have? And all known algorithms that can support query 1 can also support query 2. There's no reduction. So I would love to see a reduction to say that if you can support query 1, then you can support query 2, but I don't know how to do it in a black box way. Anyway, so let me talk about like if you have only insertions or only deletions. When the algorithm is only insertions or only deletions, what we typically do is we measure the running time in terms of the total running time, the sum over all the updates. Because when you insert, you can only insert up to m for some m, and you delete, you start with a certain number of edges, and you can at most delete all of them. So this makes sense. If you have only insertions, only recently there was some progress in this problem. This is a very annoying problem I spent some time on. This is to try to have a very small update time. And there's this nice paper that shows that no matter how many insertions you do, the total update time over insertions is no more than n squared log n, which is great if you insert up to n squared edges, but because on average or amortized, your running time would be log n. But unfortunately, this algorithm also runs in n squared log n time if you insert n edges. So this is not good. So this is great for many insertions, and this is the best running time right now for a small number of insertions. So if you insert m edges, the total running time is m to the 4/3, but this is randomized. And there's a different algorithm that's deterministic. For deletes only, recently was shown that you can basically get m polylog n, or m to the 1 plus little o of 1 total update time, which means that your amortized running time for deletions is great. But the moment you allow both insertions and deletions, it becomes pretty bad. So in other words, if you do only deletions, you get basically polylog n amortized time, and for only insertions, you get m to the 1/3, which is much better than recomputing from scratch, which would be linear time. Fully dynamic, the best known solution is to just recompute the strongly connected components from scratch when you do insertions and deletions. And we'll show that under strong ETH, any fully dynamic algorithm that can answer the queries, is the number of strongly connected components more than 2, will require linear time, basically, which is might as well recompute from scratch. Again, maybe it should say the strong ETH is false, or maybe these problems are hard. I don't know. One of the two. Okay. So the reduction will also be super simple. So I'll just do it in one slide. But let's set up the framework. Again, there's a typo here. This is the one is not there. I copy pasted and the typo remained. It's okay. So it will be very similar to before. We'll create some initial graph, and then we'll have a stage for every vector in the instance. In the orthogonal vectors instance, this 1 is not there. Imagine is gone. So you insert the edges. You query, is the number of strongly connected components more than 2? If it is, you return there is orthogonal vectors pair. Otherwise, you delete the edges. Same idea as before. And the same sort of stuff holds. The number of edges becomes n times d, which is small. So subquadratic in M becomes subquadratic in n for orthogonal vectors, which refute strong at th. So I will just show you the construction now. It's the same idea as before. This is the graph after pre-processing. You're given an instance of orthogonal vectors. For every vector, you create a vertex here. There's n vectors. For every coordinate, n to the little of 1, you have these nodes over here. You have t, which is some node over here isolated, and you have a node s, where every vector node has an edge directed towards s, and every coordinate node has an edge to every vector that has a 1 in that coordinate. Very similar to before. Okay, you throw this graph into your data structure, it does some pre-processing, and now you start a stage for every vector. We start a stage for vector v, and the updates will be in red. First, we're going to add some edges from s to the coordinates. These edges encode the vector. They say, what coordinate is the vector 1 in? You put these edges, just like in the previous reduction. And over here, you add bidirected edges. These bidirected edges are for the coordinate that the vector is 0 in. Okay? And that's all the edges that you add. You add exactly d or 2d or something, at most 2d edges in here. First of all, there is no path from S to C if the current vector has a 0 in C. Because in order to go from S to this part over here, you can only go to a coordinate in which you have a 1. And then you jump to some other vector and then go back to S. But then again, you can only go to a coordinate in which you're 1. So you'll never go to a coordinate in which you're 0. And similarly, because T only has bidirected edges to coordinates in which the vector is 0, there's no path from S to T. T, on the other hand, is in a strongly connected components with all the coordinates that the vector has a 0 in. And S is in a strongly connected component with all the vectors that have a 1 in the coordinates that V does. Right? U and S, for some U over here, are in the same strongly connected component if V and U share a coordinate in which they're 1. So they're not orthogonal. So in other words, if all the vectors over here are not orthogonal to V, then this will be a full strongly connected component. And otherwise, if some vector here is orthogonal to V, then it will not be in any of these two, and it will be isolated. So there will be more than 2. So the number of strongly connected components is 2 if there's no vector orthogonal to V, and it is more than 2 otherwise. So we do this to you, remove after we learn that it's not orthogonal to everything, then we just remove its edges and so on, and move on to the next vertex and so on, and we solve orthogonal vectors. Okay. I really wanted to show this for, is the number of strongly connected components more than 1, but I cannot make it a single component, so more than 2. So maybe that problem is easier. Questions here? Yeah.
Sorry, you mentioned this earlier, but for the
For connected components, I mentioned it in the beginning. Connected components is, unlike strongly connected components, has a very nice algorithms, dynamic algorithm, with log n times log n squared, right? So that's easy because we can put trees in there, and strongly connected components can be captured by trees. Anyway. Okay. Yeah.
So maybe I should bring this up, and maybe people here know more than I know, but there was a long-standing open problem in finite model theory if you can maintain the strongly connected components or actually transitive closure, if you can maintain the same first order logic.
Yeah.
And that was closed about, I don't know, 6-7 years ago by Tomasz Schwentik and some of his students. So what it means is that if you have a structure that represents your transitive closure, when you insert a new edge, then you only need a first order logic expression to compute the updated transitive closure. When you delete an edge, you only need a first order logic expression to update your transitive closure. But what you're saying, I'm showing here is that the actual runtime of those first order logic expressions, they have to be, correct me if I'm wrong, quadratic, right? And they have to be
Linear. Well, linear in the number of
linear in the
edges.
number of edges, right?
Yeah.
So you essentially don't gain anything except the satisfaction that you can express it in first order logic.
That's so cool. But maybe we'll give some reduction to orthogonal vectors somewhere. That would be interesting too. But yeah, that's interesting.
Let's say something about parallelism though, right? Because if it's first result, it's an ACC also very parallel.
Very good. Yeah.
But yeah, that's true.
That's exactly right. This is the class dynamic FO,
Oh, okay.
introduced by Neil Immerman in the mid-90s. And they got that you can maintain in a first order way undirected reachability. And then they had spanning trees and insertions only. And it was open for insertions and deletions, and that was all. But first order queries are horrible, right?
Yeah.
Essentially, the trick, as Thomas explained to me, the trick is they do matrix inversion. So they manage to express matrix inversion in personal logic somehow.
Exactly right.
Which is beyond what I know.
That's it's a computationally intensive task, matrix inversion.
There is a question, what is the reality of the auxiliary predicates? It's binary or ternary. For undirected, they can do it in binary queries.
Okay, that's very cool. We should have a reading those one.
This
Just
is
send
a
you
beautiful,
the reference.
this is a beautiful construction.
Thank you. Thanks. Okay. And the final thing I want to show you is that diameter is even harder. So diameter, instead of linear time per update, you have to do all pair shortest paths. So you have to do mn, number of edges times the number of vertices per update, again from strong ETH. Okay, so a preview of let me tell you about diameter. So we have an undirected, unweighted graph, and we maintain insertions and deletions. And we want to know the current diameter of the graph. Again, the diameter is the largest distance, and I'm okay with approximate answers. In particular, 4/3 approximation, 1 plus epsilon approximation, good approximations. The trivial thing again is you recompute the diameter after you query an update, which is mn time if you use BFS from every node. And we show that 3OV, which I defined earlier, the 3 version of orthogonal vectors, if you assume it can't be solved faster than cubic time, then you need mn time. So instead of 2OV, now we do 3. All right. 3OV, let me remind you, you have 3 sets A, B, C. The dimension error is again here because I copy-pasted into the little of 1 dimensions. We want to know if 3 vectors, 1 from each set, are orthogonal. And the hypothesis is it needs cubic time. The setup is, again, we make some initial graph for every vector in the set C. So the initial graph will encode the vectors A and B. And then for every vector in the set C, we'll have a separate stage. We'll insert, remove the 1 here, enter the little of 1 edges, and then we create the diameter algorithm. If the diameter is more than 4, we'll return there's an orthogonal triple. If it is less than or equal to 4, less than or equal to 3, then we continue, and then we delete the D edges and we continue. We keep going. So that should be at least greater than or equal to 4 here. Again, the number of updates similar to before is ND, as is the number of edges, which is n to the 1 plus little o of 1. And if you could do better than mn here, that would be better than n, so n squared per stage. There's roughly n stages, and so it would be better than n cubed overall, so that will refute 3OV. So we'll go through the details in a second. Okay, let's start with the initial graph. For the sets A and B, we create nodes for the vectors in A, nodes for the vectors in B. Now for the coordinates, we're actually going to create two sets. We encode the vectors in A over here to this coordinate. So for every vector and every coordinate, we'll put an edge whenever there's a 1. And the vectors in B are encoded here. For every vector and every coordinate, we'll put an edge whenever it's 1. There's no edges in here. Here we have this gadget, a path of length 2. I'll tell you what it does, but basically Z, this node Z has an edges to everything in here, Q has edges to everything in here, P has edges to the middle, and we have this edge here. The entire purpose of these nodes is so that every pair of vectors that is not one here and one here is a distance at most 3. Okay, so these pairs, 2 nodes in here are distance 2 through this node, 2 nodes in here, distance 2 through this node, a node in here and a node in here is a distance 3, like this, similar like this. To go to here, you go this way. Anyway, every pair of nodes that is not one from the left and one from the right are a distance at most 3. So if the diameter is more than 3, it will have to come because of a distance between this a node here and a node here. This is the entire thing. So ZPQ ensures that all distances are at most 3 except for those between A and B. Okay. All right. So now we start a stage. For every vector in C, we're going to insert edges in here. What edges do we insert? We just, for every coordinate, we check does that vector have a 1 in that coordinate, we just add an edge there. So we add some edges. And it will basically, there will be a matching, which encodes the vector x in C. It says which coordinates does it have a 1 in. And this only inserts D edges, and we're done with this. And now we ask about the diameter. If for every triple of nodes, U in here, V in here, and X in here, they're not orthogonal, that means there's some coordinate so that U is a 1 in that coordinate, V is a 1 in that coordinate, and X is a 1 in that coordinate, which means that the edge CC over here also exists. So if for every pair over here, they're not orthogonal, there is a path of length 3. If for some pair, this U and V over here, together with X, they are orthogonal, then there's no edge here that will create a path of length 3. So the only way to get between them, the shortest path will be of length 4. So therefore, the diameter is 3 if there's no orthogonal triple, and is at least 4 otherwise. So distinguishing between 3 and 4 will solve 3OV, which will solve SAT, and we'll be happy. And again, it's a very sparse graph. There's ND edges, ND insertions, and so on. And you get now, because the lower bound is no longer quadratic, but it is cubic, after the n, because we only have n stages, 1 for each vector, each stage must take quadratic time instead of linear in n. And quadratic, when n squared means mn, because m is the same as n here. So beating mn would be quadratic time for every stage, which would be cubic time for the whole thing, which would refute 3OV, which would refute strong ATH. Okay. So that's the entire construction. Questions about these things before I conclude? Yeah.
I don't know a lot about this area, so this might be a dumb question. But if you knew, for instance, that the degree were bounded, because all these constructions seem to rely on a node that has roughly n edges coming out of it, do you think that some problems become solvable in that setting? Or
I think you can create constructions where all the degrees are bounded. You just have to add more gadgets. And also 3 versus 4 can become 3D versus 4D for any D that you pick. You can have additive error added in there as well. There's all these complicated constructions. And we even have a construction where instead of 3 versus 4, it's 2 versus 3. And it's 2D versus 3D, all that stuff.
Okay, so bounded degree won't save us here.
It doesn't.
Is there a notion of dynamic preserving reduction? Like if you can maintain one thing efficiently, then you can
Oh, there's some reductions like this. Yeah, so for example, there's a reductions that reduce dynamic maintenance of like maximum matching in weighted graphs to maximum matching in unweighted graphs dynamically. There's other dynamic reductions as well. Yeah, there's notions like this.
Have there been any attempts to create such reductions automatically? So in NP hardness, please, there's certain attempts and successes of finding automatically gadgets.
We haven't done that, but I want to do that. That's a good question. Yeah, we need to define certain classes of gadgets and then search for these gadgets and like combine them. I haven't. That would be great. All right. As a recap, different conjectures or hypotheses seem to be better for explaining different theories. Usually that's because of a different quantifier structure. This is probably where logic will come in for you guys. Some of these problems like orthogonal vectors, they exist, and then for all. Others are, for all exists, which is basically the same thing, but or exists for all exists, and so on. Depending on your problem, you can kind of gauge what problem you should pick to have a reduction from, if a reduction exists. For these problems, all these problems that I mentioned here, you get different conditional lower bounds, assuming what different problems. Threesome gives the weakest ones, but it seems like a different conjecture from the other two. BMM and OMV and Seth imply the same conditional lower bounds for some problems, but not for all. And OV implies things for diameter, and so on. If you add all pair shortest paths and assume that it requires cubic time in the number of vertices, then you can get more conditional lower bounds. For example, for maintaining the shortest path between S and T, which are fixed vertices under edge weight updates, for example, or a weighted max weight matching and so on, and then you have to make n squared time per update or query, and so on. There's all these reductions you can create. Many of them are pretty simple. You might have some extra gadgets that are annoying, but it's not too bad so far. Yeah, so that's all I have for today. If you have any questions, go ahead and ask.
Are there examples of such reductions that can distinguish between amortized and worst case complexity?
Yes. So in particular, the question is, are there reductions that distinguish between amortized and worst case lower bound update times? So yeah, in particular for partially dynamic algorithms, often when you only do insertions or only do deletions, often amortized, you can get really good algorithms. But the same conditional lower bounds hold in the worst case, partially dynamic case as in the fully dynamic case. Roughly because when you do insertions and deletions, if you have these sort of reductions, you insert some stuff, you ask a query, then you delete some stuff. You can simulate that with a partially dynamic algorithm by, you insert, and then you roll back the data structure to the point before you insert it. And then it becomes only an insertion, only data structure. And this only works for worst case update times, but it doesn't work for amortized. Phil, you had a question?
Yeah, I was going to bring up the problem of the shortest paths with 2 weights. NP hard, if the weights are binary. I'm trying to remember. I was looking that up. But for the case of approximation, with respect to one or both of the weight functions, is
I don't remember offhand, but there was some paper about something.
Yeah,
like this.
I'm vaguely remembering.
Yeah.
You mean a lower bound, you think?
Yeah, there's some conditional lower bound for some variant of this, but I don't remember. I have to look it up.
Yeah, okay.
So in database, to deal with the difficulty of updating one by one, you could try to batch up in a to flash the batch, and then you get kind of a smooth curve. If you have everything, then you basically it becomes an offline problem.
Yes.
But these reductions.
Oh. For batch updates, I guess, yeah. But so often batch updates in the algorithm sense give you better amortized times. Sometimes they can be amortized, but so for some of these problems, there are algorithms that do a little better when you allow batch updates, and so you won't get exactly the same conditional lower bounds. But I haven't tried too hard.
But here in your reductions, you actually know all the insertions and deletions in advance.
I know exactly everything. Yeah, I know everything in advance. And you know everything in advance, except for an OMV, which you supposedly don't know it.
So did I understand correctly that these reductions also apply if you consider only insertions?
For worst case update time. So if you know that in the worst case, some of these update times will be very bad. They don't apply for amortized. So, and there exist better algorithms, for example, for reachability in the amortized case. Because in fact, you can do it in total linear time, in incremental.
So a common theme is that you're putting a lot of bridges among these problems. So say I solve reachability, then I can solve Seth. I solve SCC, I can solve Seth. So has that happened for some major hypothesis before? Like you actually found that fast algorithm, thereby resolving the major problems?
Yeah, kind of. So for example, there's a lot of cases where you need to solve a structured version of the problem. Like if you want to do min plus product, but you know something about the matrices. Maybe the matrices have bounded differences, so they're close by entries are close. And the matrices, then it wasn't known whether you can get better than cubic time algorithms for min plus product. And we tried to get a reduction and we failed. And therefore, we got an algorithm because we knew that there was a reduction from Boolean matrix multiplication, so combinatorial lower bound, but we couldn't get a better one. And therefore, we knew that in order to beat cubic time, we needed to use matrix multiplication, and we did. And we actually got a better algorithm. So this happens a lot. You try to encode something, it doesn't work, you see why it doesn't work, and then you try to get an algorithm to exploit that. And some conjectures were refuted. There was some conjecture about, so we actually had in our paper, about equations. Remember this in the listing triangles paper? We had some conjecture about the equations over a finite field and so on, something that you can't solve a system faster than the field size to the n time, where n is the number of variables, and then that turned out to be false. But then people changed that hypothesis to threesome, and the same sort of construction worked, and now the conditional lower bound still holds, even though the original hypothesis we used was false.
You mentioned a version of the Boolean matrix multiplication hypothesis. I mean, there are quite a few database theory papers that use a different version. Namely, they state that Boolean matrix multiplication cannot be done in quadratic time. Is this a, no? I think all these papers on enumeration of conjunctive cyclic conjunctive clears or free conics with linear preprocessing and constant time enumeration. No? I think they often use.
Is quadratic time in the number of entries or in n in the domain? And then, okay, so it's saying that there's no linear time algorithm for the problem, right? When the matrices are dense. So you can use that and get, in the same stuff holds, right? The same kind of reduction still holds, and you'll get some conditional lower bound for this problem.
Reinhard,
Dan wants to correct.
if I'm right, and people here might know better than that, I think the conjecture that the Houston database paper says that you cannot compute a Boolean matrix multiplication in time n squared.
Exactly. Yeah. Sorry, then I didn't manage to convey the message that I wanted. Exactly. I think that's for example, in Benny Kimmelfeld's papers, I think they use this kind of hypothesis.
Yeah, we use stuff like that too.
But
I don't know
how
how
does
the
this
leaf
fit into the
works.
picture? Because it's yet another
So there's versions of this thing. You can have versions. This cannot be done in less than n to the omega, whatever omega is for matrix multiplication, and if omega is 2, okay. We have this. You can say triangle detection cannot be solved in linear time, which is almost the same as Boolean matrix multiplication can be solved in n squared time. So you can use these, and the same reductions will work, and then you get a different lower bound from that, different running time.
Is this a stronger assumption to say not feasible in
It's a better
quadratic
assumption.
time?
I mean, it's a better assumption than assuming it requires whatever and cube time.
Yeah, so it's stronger.
It depends what you mean by strong.
I
It's
assume
better.
more.
No,
You assume less.
assume less.
You're assuming less. We assume more.
Sorry, not feasible. Yes, you're right.
Yeah.
Let's get back.